Oh, Breno, by the way, this is the same. Okay, okay. So this is I'm just about to say that I will present this at work also, like next week. So you guys are my test drive, basically. So let's go. So the theme of my presentation is co-recursion or circular programming, and the title for it is laziness at its peak, right? Because as you guys will agree with me later, this is a farming example of how laziness can be useful and at the same time confusing. And my the point is to make you uncomfortable. You're going to read the code and you're going to not understand what's happening, and that's kind of the purpose of it. So
Laziness
let's go.
already makes me uncomfortable. But anyway, keep going.
Okay, so the theme is a simple problem, right? And I will provide for that problem a mind-bending solution. So that's kind of our journey. That's the roadmap, right? Okay, so what is the problem that we're gonna tackle today? It's composed out of three things. The first thing is a linked list. So very classic computer science concept. I don't have to explain it. The second requirement is that we want to find the minimum element in the linked list, and we want to swap every single element in the list with the minimal amount. And we want to do that in linear time, right? So that's what we want to do, just that. And then you may ask, okay, I know how to do that. The solution is called, okay, go Nathan. Oh yeah, pointers. But I have a feedback for that, right? Which is I don't want to use that today. I am kind of not in the mood, right? So I want something a little bit fancier, more functional, maybe people would say. And I'm going to provide a spoiler about this solution, right? Because I'm a good guy. This is the solution for it. Just this. This is the solution for that problem. And I'm going to give you guys, I don't know, a water break to try to figure out, to understand what is on the screen right now. Here's a tip. Um, Pay attention to this part of the code, right? Specifically the last line of the highlighted part, right? So as you can see, the solution involves something called result and something called feedback. And feedback on the left is the same feedback used on the right. So then the question becomes, okay, but how come, right? How exactly this came to be? Does that make any sense? Right. And the answer is yes, surprisingly. But it's an adventure to get there. So, the key concept that makes this possible is something called laziness. This is the key idea that makes this entire thing possible. So let's explore a little bit of laziness a bit. Okay, so in a loosely manner, I'm not gonna say like the formal definition of what is laziness because that's gonna be a little bit complicated and time consuming. So I'm just gonna summarize it as, do I really need it? Right. Every single time as the compiler is doing stuff, it's asking this question. It's asking the question that, do I need this to proceed? To proceed to what? To whatever the user is asking me to do. And then this principle allows us to have some cool properties. These properties can be acquired using something that is not laziness, but one of them that laziness also provides cool properties such as short-circuiting. So if you have an expression composed of a lot of booleans, such as an AND logical operator, and you don't have to do all of them, right? If you discover that the first one is false, then you're done. But unfortunately, although it can be cool, it's very counterintuitive because when you are studying computer science, we usually have a strict evaluation in mind. So it can be kind of hard to follow what GHC is doing or whatever other lazy compiler is doing. Okay, so this is my summary of laziness that we need to know. There is a second concept that I need to put a little bit of time on it, which is thunks, right? Because we are going to use Haskell for this. Thunk again, in a loosely manner, it can be defined as a value yet to be evaluated. So we have something which we can imagine it is a pointer to a memory region. And this thing is something that is yet to be evaluated. You don't know the value yet. And again, because we are lazy and we're going to ask if we need that to proceed, this can be not evaluated at all sometimes. Right? And this set of thunks actually make what we call a graph. Right? A graph of thunks. I'm not going to go into much detail about it, but that's what you need to know, that thunks, they make a graph, and we want to fold this graph doing what we call a reduction process. So it's basically doing substitution and like, again, this is very loose because there's like eta reduction, beta reduction, and much more. But I just want to make it simple just for the purpose of this presentation. So what we're going to do now, you're going to try to mimic, right, what GHC will be doing. But it's not complicated as it may seem because I have the steps right here. Right? So these are the steps. You're going to ask if you need it. You're going to reduce it then. And then you're going to repeat this process endlessly until you finish what you want. So let's suppose that I'm going to provide to the function solution a list with 3 elements. 1, 2, 3. And again, solution will provide me a list with all the elements in the list being 1. Because this is the problem. Right? So if you look at the code on the left, you're going to see that we have corecursion, getMin, which are functions below, and then we're going to have a list with 1, 2, 3. So this is kind of what we want, right? This is kind of what we want, and we know by looking at it that the result of that is called actually result. That's the label for it. Okay, but what is result then? Well, result is it's a part of the answer of that function getMin, right? So we can kind of rewrite it like this. That makes sense, I guess. So next step, I would just make it a little bit easier to read later. So I'm just rearranging stuff. I'm adding more names to my thunk list. So the result is the first of whatever the getMin function provides, and that provides a tuple for you. And because T1 actually asks for feedback, I'm also describing what feedback is. Right? So now we need to discover what is T1 in order to get result. Right? So we're just going to read. T1 is equal to getMin, and getMin has 2 cases, right? If you are a list with only a single element, or if you are a list with more than 1 element. And because our list has more than 1 element, we're just going to go to the second case, naturally. Okay then, so we're just going to replace things, right? Basically substitution, nothing too fancy. And then we're going to discover that T1 is actually that tuple right there, right? Feedback, cons, rep, whatever those are, and min of 1 and m prime, right? Okay, so we're just going to go to our thunk list above with result and feedback and replace those. That's it. Instead of first of something and second of something, I'm just going to reduce it. Naturally. Okay, but then we have a problem, right? Because now we need feedback and we need rep. We know what is feedback, by the way. It is a min of 1 and m prime. But we also need an m prime, right? And after feedback, we have a cons operator with the rep. So we need to discover what is rep and min prime in order to continue. So we need that. So we're going to ask our previous thunk, which is T1, and then T1 will say that, oh, rep and m prime, they are the answer of another getMin call. Okay, so let's just create another thunk called T2. Let's put rep and m prime there, rep being the first and m prime being the second of whatever T2 is. And then we're going to call it getMin again. GetMin, it asks for a list. This list has more than 1 element, so it's again the second case. Easy. Just substitution, again. There's a catch here, which is important, which is renaming stuff, right? So the function getMin actually creates rep and m prime all the time. But this rep and m prime of this round, they are different from the rep and m prime of the previous round, right? So then, just for the sake of simplicity here, I'm going to rename them artificially to rep2 and m prime twice. And then we discover that T2 is feedback with the same feedback, by the way. This is another important detail. The feedback that we are using here, it's not being renamed because it's the same. We are just passing it around over and over again. So T2 is feedback cons rep2 and min of 2 and m2 prime, or m prime twice, let's say. Okay, let's swap that in our thunk list then. Okay, so then we know now that rep is actually feedback cons with rep2. Feedback is min of 1 and m prime, and m prime is the min of 2 and m prime twice. So then the problem is, what is rep2 and m prime twice? Okay, so let's ask T2 again. T2 will say that is, oh, this is the result of another getMin call, this time around with a list of with a single element. That's important detail. And then, okay, so let's add that to our thunk list, no problem. And now we need to know what is T3, right? And then, okay, just pick the functions, swap the values, and you're going to discover it is this, which is different than before. And then, okay, let's just swap those in our thunk list. Let's just reduce it. Then we have this thing, and we don't have any other function calls this time. So if you see, m prime now can be evaluated to a value because it's min of 2 and 3. Rep2 can actually be swapped in the where it's being used because now you actually know what it is also. And that's it. And now feedback can also be evaluated, right? Because it's a min of 1 and 2. So we're just going to do that. And then if you swap everything else after that, the result now has a proper answer, which is a list of 3 elements. And the 3 elements are the same, which is 1, which is the minimum, right? Which is the minimum. So we started with something that is a list of 1, 2, 3, and now we have a function with 3 of length with all 1 elements, which is what we wanted in the beginning. Okay, so all this process that I just described, it has a name called Corecursion, or circular programming, as I saw in the initial post that I found about it. And this is known as the recursion's dual, right? So it's kind of like the counterpart of recursion. And it is counterpart because recursion picks something and tries to divide and conquer it until it reaches a base case. Corecursion, on the other hand, it picks a base case and expands on top of that. Right? It starts growing on top of what it firstly receives initially. In my mind, for instance, recursion is kind of like a negative feedback loop because it's trying to be more stable as we go towards the base case. And in contrast, the co-recursion is kind of like a positive feedback loop. Each round, the smaller perturbation starts to grow the data, right? And something very cool about co-recursion is that it handles a little bit more naturally infinite data structures, or more complicated data structures because of that. So that's a summary that I want to provide about co-recursion. And then okay, but that's a simple example, right? It's just a linked list. So what can we do about that with this tool? And then here we have a more complicated example, which is a binary tree, right? And it's basically the same thing as before. We have the getMin, we have the solution. We just don't have the third auxiliary function because that we can do it in this manner. It's such the same confusion as before. And then that's great, right? We can apply the same thing. So you have a binary tree, you want to swap all the elements in linear time to the minimum of all of them without using pointers. And then you can do it like that. Yeah, but then let's suppose that you want to do something a little bit more while you are doing that, right? Let's suppose that you want to print something while you iterate throughout the data structure, right? Now that we know that the getMin function is the function responsible for iterating throughout the thing, we can just naturally add an IO to it, right? We can just do a little bit of denotation, like do a little bit of massaging to add stuff and print stuff along the way, and then that's fine. But then we stumble upon a problem, which is that this thing doesn't type check anymore. All right. So if you put this code on your editor and ask to compile it, it's gonna complain a lot. And but there's a solution to that too, right? There's a solution to that too, which is this, right? So I just changed the solution function. If I go back, you guys can see the get bin function is the same, just the solution function is different, and it's this now. And it has a special thing now, which is very uncommon to see, which is this, right? So this is a special syntax sugar called mdo that is using a fixed point combinator, but it's using that in a monadic context, right? And so it's basically the best of both worlds. You can do co-recursion if you see that it fits better for your problem, and you can use powerful actions such as maybe IO, any sort of transformer, and stuff like that throughout the co-recursion process, right? And what is very interesting is that there's a lot of things in the universe that explores some sort of recursion, being co-recursion or natural recursion. And one of them, it's nature, right? Nature loves to do this all the time. It does recursion in a very unexpected manners, I'd say. And then we have something like this, which is an analog device called an operational amplifier, which naturally has something recursive going on because the output is being connected to one of the inputs, and it's very weird. And because we have access to something like an mdo block, a monadic recursive do block, we can do stuff like this, right? We can say, okay, let's say that I want something like a signal. It can be, for instance, electricity, and it can be in the time domain or in the frequency domain, so you can have a complex number. And let's suppose that I want to have a circuit that I provide an input and it provides me an output. And then you can have something like this, in which it's basically, it is Haskell, this works. And then you can say, oh, I want a circuit with this topology, such as this one, which is what we call in electrical engineering as an inverting operation amplifier topology. And then you can provide the resistors, you can provide the model of the operation amplifier, you can provide a DC signal of 12 volts, and then it's just gonna calculate to you what exactly is the output of that. And I'm not showing this right now because it's I don't think it's worth it. But you can say that this is a category, and then you can compose secrets together. You can put the output of one as the input of the next one, and you can have a chain of different topologies of operation amplifiers together, exactly as we do in hardware. And everything like with compose, like with the dot operator in Haskell. And they will be calculating their things recursively using internally the mdo thing, and that's and I just thought that this was too elegant to not share. And that's about it. And that's the end. Questions?
That's cursed, man. That's cursed. This Fibonacci definition. Can you go back to the operation amplifier?
Yes.
Yeah, I wanted to just, I guess, understand the result there. What does signal to nodes mean? Because if I understand correctly, the C1 simulate DC12 line. This means that you're putting a 12 volt DC signal in the input, right?
Yes.
What
Okay.
is the output there?
Okay, so I can explain the output. So the output is a tuple of two things, and the reason why is because we have two nodes that matter for this recursion, which is the Vout node, and it is the node that is connecting the R2 and the R1, which usually we call Vx or something like that.
Ah, okay.
So the first member of the tuple is Vx. So it's what is the voltage on that node? And as you can see, it's 0. Almost 0, right? Almost 0. It's 299 like 10 to the power of -4, so it's kind of 0. And the other member of the tuple, that is the V out answer.
Which is like
So
minus 60 volts.
yes,
Oh, that's really, so it solves all the nodes in the circuit.
yes,
That's nice. What is does R1 and R2 matter in this case,
yeah, they
or
matter
does it
because they
cancel
need.
out?
Yeah, I think it's R1 is like 10k ohms and R2 is like 50k ohms.
Okay, yeah, because I remember there are situations where the values kind of cancel out, so sometimes the actual values don't matter. But that's really cool.
Yeah, and they it is using the monadic fixed point combinator inside. And yeah, that's pretty cool. So any other comments, questions? And by the way, this thing works. This Fibonacci definition works.
Yeah,
Yeah,
I
I've
was
seen
going to
this
say like
before.
this is very useful because you have the two. Because like if you think of a series, like I think of a I think I was talking the other day about ODEs, right? If you
Mm-hmm.
think of a series, you're literally just flattening the thing that you cannot transform in a tail call. I think in Fibonacci you can, right?
Yeah.
But this is really interesting. Like, how would you? Okay, I'm not gonna ask about like specifics.
Okay. Go.
Um,
But just go for it.
but like, what is the idea behind transforming a random function? Like, if you pick a template of a function that is not tail call, so it has like think of Fibonacci that have two things to sum as the last argument. So
Mm-hmm.
how do you transform something like that that has like base cases into using Corecursion?
Um. Okay. So going back to this example here. No, not this one. It can be that this one, but I want to go to this one.
Might be a stupid question, by the way. I just
Go. No, it's not a stupid question, by the way. Okay, what I want to show is that although co-recursion, like I said, it expands on top of what you give to it, it
Mhm.
kind of has a base case if you think about it. Because if you look at the code back, this code, the get min with the single element in the list, this is the base case, right? So co-recursion, it has the ability of tackling potentially infinite data structures, but it needs to do that in a finite number of steps.
Uh-huh.
So the way that it does that is you need to have at some point you need to stop calling things. In the case of Fibonacci, that was not happening there. You're gonna have to use a take on that function to provide like I want the first 5 Fibonacci numbers. Then you do
Mhm.
take 5 of that. Here, that's not what's happening. Here, the getMin function is actually putting a stop point for the Corecursion to stop expanding. Because what is actually expanding the process is the thunk list, right?
Yeah, I get it. Hmm.
So it kind of has a base case, but I just don't think it's good because we want to differentiate between normal recursion and co-recursion.
Hmm.
So I think it's more natural to think about the expansion process, but if you want to think about a base case, it has one. And something that I should mention because of Nathan is that this thing, the original author of the blog post that I found talking about this, he said that apparently this is also can be called a form of continuation passive style. He said that. He said that this has another name, and because I'm too dumb to understand that, I didn't understand what that means. But apparently it has this third name, continuation passive style. Yeah.
Hmm. Yeah. Mm-hmm.
Mm. Okay, so that's why he said the first link is the original author blog's post. The second link is my attempt on writing about this, and the third is the one of the papers that I was recently reading that explains the mdo block. And it's I explored also doing my final graduation project, by the way. So I didn't come with this just for this presentation. I spent like weeks, months understanding what this is and making this library.
Yeah, I remember from your thesis that you ran into some problems with the convergence
Yeah,
of the functions. So I was wondering, maybe this is something that is more useful. Like this is really a really cool application for sure. But maybe this is something more natural for just like discrete, like well behaved
yes.
data structures
Actually,
like
the
the
author
tree.
says that. So let's suppose that you have you have like some digital I don't know mux switch with a reset signal and stuff like that, and you have a lot of these hardware stuff. We have recursions naturally. Like
Yeah,
it's
yeah,
kind of weird.
exactly.
And then for these specific applications in which it's more natural, like for the engineer to write something in a recursive manner because he doesn't know. He's an engineer. He's not a programmer. He's not a computer scientist. The engineer just knows how to use the hardware and the laws
Yeah.
behind it. Uh, so if you want to model exactly that idea, you can use this for that.
Yeah, interesting because I was actually thinking about a similar thing with digital, like digital circuits, but in Golang with like channels and stuff.
Hmm.
Because I think that the underlying, not the underlying mechanism, but it allows you to express similar things at the end of the day. So
Yeah.
this is an interesting parallel. Have you tried doing some digital circuit stuff with this? I think this would be really cool. Like make your own digital simulator.
No, I didn't try it because um, this library is incomplete because it's not like literally using the mdo. It's using because we have three steps in this fixed point madness. We have the normal fixed point, which took me a while to understand and get comfortable. Then we have a middle point, which is the monadic fixed point, which is actually called the mfix function. And then we have a syntax sugar that uses mfix called mdo. While I was developing this library, I got stuck between translating between mfix and mdo. So this thing is actually using mfix. It's not using mdo yet. But I consider to be using it. I just don't know how to do it because mdo is just a syntax sugar for mfix.
Yeah, yeah. I guess it doesn't really matter as long. Does it show up in like the interface, the domain specific language? I guess for like composing the circuits.
Uh, no, we
Like
don't.
if you have two circuits, you can just compose them without
Yes.
any like. Oh,
Yeah, you can
that's
just do
nice. Yeah,
compose
it
and
doesn't. I think it doesn't really matter then that you're not using them too. This is really cool.
yeah. And because I was stuck, I started implementing other type classes for the circuits. Like I showed that it is a category. I also showed that it is an arrow. That was fun, but I'm still pissed because I couldn't make it to MDO yet.
Have you tried? Don't really know how to express this. I'm wondering like how often did you run into infinite loops doing this? Because I guess this is a
Oh, a
situation.
lot.
Because in this the thing that I'm doing, my problem is not like infinite loops. It's just deadlocks because you're kind of having multiple processes and they get
Yeah.
locked.
Mm-hmm.
Yeah, your problem is very complicated in my opinion. Because I can notice for a fact that oh, it's just infinite recursion because it's not stopping. Yours, you don't kind of know which channel is being deadlocked.
Yeah, there's yeah, it's tricky. But it's like the two sides of the coin, you know. It's like the same problem, kind of expressed in different ways. Like you
Yeah,
didn't get your data dependencies right.
yeah. So, any more comments, questions about this? Go. Yes. Yes. The mental model for this. Um, yeah. I got your point. But unfortunately, the answer for that is that I don't. For me, it's very. I couldn't wrap my mind in order to be natural for me because I spent years doing just recursion. And it's kind of wild to stop thinking like that and go to the other side, like cross that line. Because this thing involves two things. In order to have a mental model, you need to be comfortable with two things. The first is the whole expansion idea that you are providing something and the recursion is like evolving on top of the data that is generating out of that, right? And the second is the laziness. So if you don't get your mind comfortable with those two concepts, like what I mean with comfortable is for you it's so natural, you don't have to think about it. It's already automatic in your mind. If you don't have these two properties kind of wrapped around them, I don't think you're going to achieve a mental model for this. And I can, for my experience, for instance, when I was using the monadic fixed point combinator, um, I got a problem because it took me a lot of extra time because my mind was still wrapped on the previous recursion model. So every single time I was doing stuff, I was, man, where is the base case of this crap? And I shouldn't be asking in this manner because, like I said, this is not the idea that you should think about it. But because I was stuck with this mental model of the normal recursion, it took me a lot longer to develop something useful, like days to write like 5 lines of code. Yeah. Yeah. Mm-hmm. Oh no, my advisor and I we did a pencil and a paper to understand this madness. Mm-hmm. Yeah. No, something that I think it would be useful to understand is that if you get comfortable with continuation passing style, it's like a piece of cake. Like not you maybe not in like a direct mapping between those two, but I think it's gonna be at least easier because you have to the same mentality of you're gonna pass a function that will call it again and again and again, and eventually you evaluate to the final result. That's why I asked you in I don't know a few months ago about it. Oh, okay. Okay, that's a good tip. Anyway, any more comments about the presentation or the
Yeah.
ideas? Go.
Uh, I think that it would be nice when you're trying to evaluate this function right there to like do some visualizations. Or one thing that I did that was nice in my thesis, I had a similar scenario when I had like to evaluate reductions, just to show like the steps all at once. I think it would be really cool to have some sort of animation here. I think it will look like very interesting. Because the
Oh,
way that
that's
I see this
fancy.
example is if you go back a bit to the yeah, whenever the first slide that showed the feedback there, I kind of got it. What was gonna happen?
And but I know you're there. How much minutes the recording is? How many minutes? Sorry, I'll guess 40. Yeah, this took a lot less than you guys presentation. I don't know if I was speaking too fast or this is just too short. Yeah, no, it took me hours only on this part, man. Like to know, okay, how can I make this as digestible as possible? Because this is it's so easy to get lost. And I did my best to try to, okay, I'm gonna compensate explaining and repeating myself a bunch of times. But man, that's so hard. This is so hard. No, that's why I said it's counterintuitive, right? It's totally counterintuitive. Yes, exactly. Yeah. And yeah, I'm so sorry for Brandon, man. We lost Brandon. Yeah. I think we can finish the recording if you don't have any more questions. Yeah, I want to make this better for next time.